Thank you, and good afternoon, everyone. I want to start my presentation with a remark which could be obvious to everyone. We are living in a matter-dominated world. In terms of fundamental physics, it means that we are, and all the stuff which is around us, is made of two fundamental particles, protons and electrons. Also, from studying physics at accelerator, we know that antimatter particles, like antiprotons and positons, they do exist, but they are created for a very limited time, and then they annihilate when they meet their matter counterpart. We also know that these particles, and even heavier particles like antineutrons and complex like antihelium, are also coming from space. So, and the studies of these antimatter particles which are coming from space, they reveal fundamental features of our universe, like existence of antimatter stars and existence of dark matter. Clearly, in order to study this type of particles, we have to go to open space. And in that respect, International Space Station represents a very good platform to study all these questions, because it provides all the necessary infrastructure for experiments addressing these questions, high precision, long duration experiments. So here I'm representing alpha magnetic spectrometer, which is experiment addressing all these questions. It was launched to space in 2011, and since then it's taking data continuously. Altogether, we have collected over 200 billion cosmic rays, which is in fact more than all other experiments combined. So, our first topic, which is really draws a lot of attention from physicists around the world, is study of antimatter counterpart of electrons, which are positons. So what we have found, that in fact the number of particles, which is represented here as a spectrum, number of particles per unit area per second, scaled with energy to the third, it shows two components. The antimatter particles, positons, produced in collision of cosmic rays, represented here by green area, and a new source. The nature of this source is not clear, but these positrons may come either from annihilation of dark matter or from new astrophysical sources. Well, clearly, to answer these questions, we are going to differentiate between two possible sources. We are going to continue our experiment and study region of extremely high energies, where we expect that the spectrum, if it's dark matter explanation, the spectrum should go back to predictions from cosmic ray collisions. Another very interesting observation is related to antimatter counterpart of protons, namely antiprotons. What we have seen studying these particles coming from space is that their spectrum, represented here by blue dots, has striking similarity with the spectrum of positrons. And this, physics-wise, means that they are coming from the very same sources. So another alternative hypothesis for explaining positrons is, for instance, pulsars, which are astrophysical objects, which can produce high-energy electrons and positrons, but they do not produce antiprotons. So this measurement, which you see on the screen, strongly disfavors pulsars as an origin of both positrons and antiprotons. Of course, our studies are not limited by these two measurements. We are looking also for much heavier antimatter particles like antineutrons and antihelium. So we have first indications of presence of these particles, but we are not yet claiming a discovery. We need much more data, which we hope to get with the improvements which we are planning to make with our detector, and collecting more data to answer these fundamental physics questions. We also do a lot of studies of ordinary particles. Essentially, what we study are the entire periodic table of elements which exist in cosmic rays, from protons up to iron and even beyond. And here we also have several very surprising observations. Namely, we know that cosmic rays, they fall into two big groups: primary cosmic rays, which are produced during the stellar evolution of stars and then accelerated in supernova shock waves. But also there is another big group of particles, which we call secondary, which are produced with interactions of primary cosmic rays with interstellar medium. Our observation shows that in fact first group, namely primary cosmic rays, they have minimum two classes: low mass primary cosmic rays, helium, carbon, and oxygen, and heavier class of primary cosmic rays, neon, magnesium, and silicon. We also studied the secondary group, which are nitrogen, sodium, and aluminum. So what we saw, that they also have two quite distinct classes within this group. And these are actually the first classification of this type which is ever made for cosmic rays. In addition to this observation, we also found a big third group of elements which in fact, excuse me, I actually messed up. So this group is they belong to the third group, which are the particles which actually consist almost half primary and half secondary. So they're a composition of primary and secondary cosmic rays. So we plan to continue these measurements for another decade. So we have been in space for 10 years. And we are planning to provide answers to all these questions which we have posed already. And maybe we have many new and exciting surprises. Thank you.